Alright, so this is COMP3132, Applied Machine Learning, Assignment 3. Okay, so let's go straight to question 1A. Okay, so question 1A. So here what I did was to detect created a kernel to detect 45-degree lines. The values of 2 are placed along the diagonal, going from bottom left to top right, with -1 everywhere else. This kernel responds strongly when it finds pixels aligned in that 45-degree direction. I applied it to the card image, using the COMP2D kernel function, and the result highlights the 45-degree lines in the image. Okay, now 1B. Now 1B, this is the kernel for 135 lines, 135-degree lines. It's the mirror of the previous one. Now the 2's are on the main diagonal from top left to bottom right. The result highlights lines going in that 135 degree direction. Okay, now let's go to 2A. Now 2A, well, here the edge kernel 1 was defined, this variable. Then I apply it to the image using this method, the COMP2D kernel, and plotted the result. The kernel detects diagonal edges because it has because it has once and -1's position at opposite corners. Now let's go to the next one. Now this one I applied edge kernel 2. This is a Laplacian filter. It has -4 in the center, and one's in the 4 cardinal directions. It detects edges by comparing each pixel to its direct neighbors. Where there's a sharp modification change in brightness, the kernel produces high values. Okay, now let's go to C. C, I applied this edge kernel 3, which was already defined before, but I apply it here. Kind of similar as the previous one, but also includes diagonals. It has 8 in the center and -1 in all 8 surrounding positions. It's a more complete edge detector because it considers all neighbors and not just 4 cardinal ones, and the result shows slightly more detailed edges. Okay, now the next one. Okay, so question 3. Did the network present signs of overfitting? If so, in which epoch? So, yes, it does show signs of overfitting. If we look at the graph here, around epoch 10 to 15, training accuracy keeps going up while validation accuracy stops improving, and it starts to fluctuate. This is the classic sign of overfitting. The model now is actually memorizing and not training. It's actually memorizing the data instead of really predicting, being trained. So it's not learning the general patterns, and this is what's happening. Okay, question 4. Write down how many layers this model has and identify their types. So the model has 5 layers, and their types are: the first one, COMP2D, 32 filters, 3x3, ReLU activation. The second one is a max polling 2D, 2x2. Third one, flattened. The fourth one It's a dense layer with 128 neurons with ReLU activation. The last one is also a dense layer, 10 neurons and softmax. Question 5. Briefly explain what is the purpose of each of those layers. Well, the COMP2 extracts local spatial features from the input image, such as edges, textures, and shapes by sliding 32 filters across the image. Max pulling 2D downsamples the feature maps by keeping the maximum value in each 2x2 window, reducing spatial dimensions and computations. Flatten converts 2D feature maps into a 1D vector so it can be fed into the dense layers. The dense layer 128 ReLU activation learns high-level and nonlinear combinations of the extracted features. Dense, the one with 10 units, softmax outputs and probability distribution over 10 CFAR, 10 CFAR, 10 classes. Okay, so now this part, this one here, I copied the original code from up there. I'm trying to find it. This one. I copied this one, but this time I added an extra conf2d layer, this method, with 64 filters, and now the model has 2 convolutional layers instead of 1. The first, with 32, extracts simpler features, and the second one with 64 features and combine those into more complex patterns. Right, let's go to the next one. So compare the results between the original model made using Keras sequential versus the bigger model with at least 1 extra layer added. Describe what are the differences between them. So, differences between them is that, well, pretty much what I said here, you know, the bigger model with extra convolutional layer, most of the time achieves higher validation, I guess, higher validation accuracy, because it can learn richer and more complex features from the images, but it trains slower. So it has more parameters. This is why it trains slower, and it can show more overfitting because it has more capacity to memorize the training data. Okay, so here 8, add a dropout layer to your model, run it, and compare the result with the previous one. So again, I used almost the same model, but here I added a dropout layer of 0.5 here, dense layer with and a dense layer with 128 neurons. So this means that during each training step, 50% of the neurons in that layer are randomly turned off. Okay, now let's answer the last question. Explain with your own words what is the purpose of a dropout layer and how it works, and briefly explain in your video in your own words. Well, basically, what is there? So dropout is I think it's basically a regularization method that randomly turns off a fraction of neurons during training, each training step. So in this case, I used 50%, like up there. So half of the neurons are randomly disabled on every batch. And when this happens, it forces the network to not rely too much on any single neuron and spread the learning across many neurons. The result is actually better, a better generalization and less overfitting. And during the test or inference, dropout is turned off and all neurons are active. That's basically it.